Hello and welcome to identifying reaction types. So in order to identify reaction types, we have to be able to identify first the parts of a chemical reaction. So on the left side of a chemical reaction, which is divided by our arrow, so you can draw a little squiggly if that helps you see it a little bit better, we have the stuff we start with, our starting materials, or our reactant. On the other side, so that's on our left-hand side, and our right-hand side, our ending materials are called our product. We've already talked about elements and compounds and how we identify those. There's some different numbers here. We talk about these little numbers called subscripts. Then we have these numbers out front called coefficients. Sometimes you may not see a coefficient. So we see those coefficients of 2. There's actually an invisible coefficient of 1 here and an invisible coefficient of 1 here. Just as chemists, we don't write 1s as subscripts. We don't write them as coefficients either. It is important to be able to tell the difference between a coefficient, which is large and goes out front, versus a subscript, which is small and comes down low. Other symbols to be aware of. We have 2 different reactants. So for example, we start with elemental zinc right here. It's a piece of solid zinc and a silver nitrate solution. So we're putting something solid into a solution. The reactants we get out are actually a piece of silver and zinc nitrate, which is a solution. So we have 2 different reactants on each side.
At this time.
Sorry about that. We have an arrow that separates the reactant from the product. So when we're reading a sentence or a chemical reaction, which is basically a sentence to us in chemistry, we would say for this zinc reacts with silver nitrate to produce or yield solid silver and zinc nitrate. So that's how we would read that. We already talked about the S, L's, and G's. They mean solid, liquid, or gas. And of course, aqueous, which remember tells us we have a solution or a homogeneous mixture. So when we look at this first group of reactions, these are all the same type. What's important to kind of notice when you're identifying these is how many things we have on each side of the arrow. So if we look at where our arrow is, in all of these we have 2 reactants and 1 product. And this is something we call a synthesis reaction. So 2 reactants coming together to form 1 product. The opposite of this, if you look where our arrows are here, is a reaction where one single thing is broken down into multiple products. So on all of these, we have 1 reactant being broken down into 2, and actually it could be 2 or more products. I should probably mention that on this one as well. We could have, oops, not there. Whoa, sorry about that. Hold on a sec. Sorry about that. We actually could have more than 2 reactants. The definition here means we really have to just have multiple things coming together to 1 product, whereas in a decomposition reaction, the opposite of this, in a decomposition reaction, we actually have definitely 1 reactant breaking down into multiple products, typically 2, sometimes more. Our next reaction type, what you're going to notice if you look at these is, if you look where the arrow is, we have 2 things on either side. If we look more specifically at them, you should notice all of these reactions have O2. All of these reactions have CO2. They also all have H2O. And all of them as well start with something that has carbon in it, a carbon fuel. So in all of these reactants, we're going to have O2 in all these reactions, I should say, we have an O2 reactant, and we have both CO2 and H2O as products. This is actually a very important reaction in our world. The last one is showing what happens in the mitochondria of your cells to produce ATP. The reaction right here with C8H18 is the combustion of octane. This is essentially burning of gasoline. First one here is combustion of methane, like we do in this room with the Bunsen burners. So these are all we call combustion reactions. They require oxygen, and they produce water vapor. So they're not actually water pouring out of these reactions, but they produce water vapor as well as carbon dioxide. If you think about this in terms of what's going on in a car, this has to do with why there's so much CO2 in the atmosphere. If we think about what's going on inside of our bodies, this is why we exhale CO2. This does produce water that you can sweat out or something like that, as well as, of course, ATP equals energy. Group 4, a little less straightforward. We kind of divide all these down the middle. In all these cases, we have 2 reactants and 2 products. Now, these don't have a whole lot in common besides in terms of like a specific element. So we can't say, oh, you know, these do actually all happen to have oxygen. It's kind of a bad example. But what these do all have in common with one another is on both sides of the reaction, we always have a free element. So in this particular type of reaction, we're going to have 2 reactants, 2 products, and we're going to have a free element always present on both sides. So in both the product and reactant side. So this is something called a single replacement reaction. In short, what happens is zinc bops silver out of the equation here. Silver ends up all alone, and zinc is now in that compound. So you can see iron doing the bopping here, copper doing the bopping here. So this is what we call a single replacement reaction. Group 5, so you'll notice that this does have the similarity of where we have 2 reactants, 2 products. This is a related reaction type. It may not be as easy to see. You'll notice you have no free elements. You have all compounds present here. So what's actually happening here is kind of similar to the last one. It just doesn't involve any free elements. So what we see going on here is potassium and hydrogen actually switch places. So now potassium ends up with sulfate. And instead of KOH, we have HOH, which can also be written as water. We have something going on here where iron and hydrogen are switching places. We have sodium replacing hydrogen here, or I should say exchanging. Silver and sodium flip-flopping places there. So we have no free elements, all compounds. So instead of a single replacement, we call this a double replacement. So we do have to be able to look at these and identify them by type. So I just want to take a quick minute and summarize that. Sometimes synthesis reactions are called combinations. I prefer synthesis. When we're identifying a synthesis reaction, we're going to have always, every time, only one thing on the right-hand side. So we know we're going to have only one product. Whereas in a decomposition, we have one reactant breaking down, so one thing on the left. So it's the difference between one thing on the right, which is one thing on the left. In combustion, we are going to have 2 reactants and 2 products. Okay, that'll be true for all the rest of these. We have to have oxygen as a reactant, and H2O and CO2 on our product side. Once you know you have 2 reactants and 2 products, I kind of check first for combustion. If a reaction is not combustion, then I determine if it's single or double replacement. In order to be single replacement, you need to have a free element on both sides. That can include a diatomic. Oops, sorry. Diatomics are considered free elements, remember? So for example, O2. As a diatomic, it's a free element, so that counts. And in a double replacement, we should have no free elements, only compounds on either side.